Hello everyone, welcome to this new lecture on velocity of separation. This is a subtopic of kinematics. So I am Dhiraj Madan and this is part of this video series on physics for IITJEE. So velocity of separation by definition, what it means essentially is the rate of increase of distance between 2 points. So let's say if you have 2 points, say A and B, right, and the distance between them, which is denoted by SBA, is essentially mod of RBA. Right? So this is the relative position of B with respect to A. I'm calling it RBA. Then essentially velocity of separation is the rate of change of RBA. So it's basically the rate of change of distance between the 2 points, how fast the distance is increasing between these 2 points. So that is known as velocity of separation. So the idea is very simple. What we'll be looking at is that we'll look at a particular problem, right? And then we'll see how do we apply this concept. So we'll need to derive an expression for this velocity of separation in terms of the relative velocity. So we'll also see that how do we do that, right? So then essentially this expression will be general enough that it will be applicable to all problems. But first to motivate, okay, that why do we even need this concept? So let's begin with a particular problem. This problem is called is from this textbook on problems in physics by Irodov. Okay, so this is the problem number 1.12. And now let me state that particular problem and then we'll see why do we need this idea of velocity of separation. So the problem is as follows, that there are 3 points, okay, and these are located at the vertices of an equilateral triangle. So there is one point at each of these vertices. Okay, equilateral triangle of side A. So basically all sides are equal, which equals A. The common value of the sides equals A. Length of the side equals A. Now they all start moving with constant velocity magnitude. Okay, so they all start moving with velocity of constant magnitude. So how much is that magnitude? That magnitude is, let's say, V. And in which direction are they moving? They are moving towards each other. So this point actually towards each other needs some clarification, right? So we'll describe it in detail. But essentially what's happening is that the first is moving towards the second. So first point is moving towards second. The second is moving towards the third, and the third is moving towards the first. Okay. Now the problem is that compute the time to converge. So this is the particular problem we need to solve. So how much is the time they will need to converge at the same point? So first of all, the question is itself implying that they are going to converge at the same point. So essentially what's happening is that by the symmetry of the problem, ultimately they'll reach a common point, which is the centroid. So we'll just see that in detail, but the problem itself is implying that. So I would first just try to read this question, try to see what you understand, and now let's explore it in detail. Okay, so if you want, you can pause the video, try to understand this in some detail. Okay, so how much ever you are able to understand, and now I'll also explain. So essentially what is happening is that, so we have these 3 points which are located on the sides of an equilateral triangle. Okay, so let's see what's happening. So there is an equilateral triangle and we have these 3 points which are located at the vertices A, B, and C. Right, so all these common sides, they equal A. Now these points, they start moving towards each other. Okay. So let's say that the first point, let's say A is moving towards B with velocity v, and B is moving towards C with velocity v, and C is moving towards A with velocity v. So now what's going to happen is that, let's say after some small amount of time, right? Let's say an infinitesimally small amount of time, they have moved some small distance dt, but now their positions are different, right? And now still they are moving towards each other, which means that their directions will also have to change. Okay. So essentially now if we look at the new sort of triangle which they are forming, right? So essentially you have, okay. So after they have moved slightly, they are essentially forming a new sort of triangle. Okay. So this triangle is essentially, again, they have moved slightly on the side. So they're forming this new triangle, A prime, B prime, C prime. And now if we look at these points, so essentially they are still moving along these sides, but now they have forming, they have moved slightly, right? So basically, they are now start moving along each other, but on the sides of this newer triangle. And now from this A prime, it moves along this new triangle and it reaches this point A double prime. So this reaches the point B double prime and this reaches the point C double prime. Now again, their directions are going to change because they still move towards each other. So let's draw a new triangle which indicates this change of directions. Okay. So once they have moved slightly, they now move along the edges of this new triangle, right? And so on. So essentially, actually their path is now going to look a bit curved. It's because essentially the directions will keep changing. So the way they are going to move is as follows, is that now they are going to move along these curved trajectories, right? Because essentially their common triangle, which includes these 3 points, that will keep rotating, and essentially the directions along which they are traveling also keeps moving. So the situation looks something like this, that they are now sort of, this triangle is also getting smaller and smaller, and ultimately they'll converge at the given point, which happens to be equidistant from all the original 3 vertices. So the point which is equidistant from all 3 vertices of an equilateral triangle is essentially the circumcenter, which also happens to be the centroid in case of an equilateral triangle. So they'll converge at this point G, which is the centroid, which also happens to be the circumcenter also. So for an equilateral triangle, centroid, circumcenter, and center, all of them coincide. So now we need to compute the time they'll require to converge at this particular point, right, which is the circumcenter. So how do we do that? So essentially, if we look at it, the velocity keeps on changing, right? So it's not an easy problem. But if we can somehow show that the rate of change of distance that is constant, then essentially it is very easy for us, because now we know the initial distance and we know the rate of change of distance. Then essentially we can easily compute the time taken for this distance to get to zero. So in order to do that, we will formally introduce the idea of velocity of separation. We have already done that, actually. We have already defined in the first slide itself. So we'll actually expand on this thing. We'll derive an expression for this velocity of separation in terms of a relative velocity. And that will also help us in solving the particular problem. Right. So let's now deviate and move towards the formal, concept description. So essentially, let's say that we have these 2 points A and B, and let us say that the distance between the 2 points, which is the magnitude of RBA, is given to us. Now we need to essentially compute ds by dt. So it's a bit difficult to just take the derivative of magnitude. So what we are going to do is that first let's square it. So S square is now going to be RBA dot RBA. And because the dot product of the vector with itself is the squared length of the vector. Now let's differentiate both sides. So let's differentiate LHS d by dt of S square, that equals the d by dt of RBA dot RBA. Okay. Now from LHS, what do we get? So basically it's the derivative of square, and now we can use chain rule. So for those of who you know chain rule is that you'll get 2s, which is the derivative of s square, times ds by dt. But on the right side, what do we have? So we have d by dt of RBA dotted with RBA. So we are using now the product rule of derivatives, plus RBA dot d by dt of RBA. Now, what is d by dt of RBA? That's the VBA. By definition, if you differentiate the position vector, you will get the velocity vector. So this is VBA dot RBA, and the other term is RBA dot VBA. Since dot product is commutative, so we can also write it as 2 times VBA dot RBA. So what we have is that 2s ds by dt equals twice of VBA dot RBA. So now from, okay, we can always cancel away 2, but what we get is that ds by dt now equals VBA dot RBA over S. Okay. So now what we get is VBA dotted with RBA over S, right? So basically this is the, now S is essentially mod of RBA by definition. And if I, divide a vector with its length, I'm going to get a unit vector in the direction from A to B. So this is essentially VBA dotted with the unit vector in the direction from A to B. So I'm going to call it E hat BA. Okay, so this is the unit vector going from A towards B. So that's what I'm going to denote it as E hat of BA. Okay, so this is essentially ds by dt. So essentially, okay, and now what exactly is VBA dot EBA hat? So essentially, if you, let's say you have these 2 points A and B, they are moving in, let's say, slightly different directions, but you can compute, VB minus VA. So let's say, that you take VB, you subtract VA. So in order to subtract, you need to take minus of VA, right? And this is, let's say, the resultant vector, which is VBA. Okay. And now essentially EBA hat is essentially the direction vector along BA. So you will have, if you take the dot product with the unit vector, you will get the component along that unit vector itself, right? So VBA dot EBA hat is the component. So VBA dot EBA hat is the component of VBA along the line joining A to B. And this is also the rate of change of distance, right? So essentially velocity of separation is nothing but the component of the relative velocity along the line joining the 2 points. So we can actually write it formally. So let's write it over here. The rate of change of distance okay, or VSEP as we call it, is the component of VBA along the line joining the 2 points. Okay, so this is the sort of result which I would want you to remember. Now let's use this result to solve the problem, right? So this result is not just for this problem, it's a general sort of a thing, but now we'll be using this to solve that particular problem we saw again. So we had these 3 points. They are moving all with velocity v along the sides of this triangle, and this triangle also keeps on changing, right? But essentially what we notice is that the rate of change of distance between the points will remain the same irrespective of whatever the configuration of the triangle is. This is because it's always the case that, that as the triangle rotates, the velocities also rotates, and essentially the components along the line joining the points will remain the same. So let's see why. Okay, so let's see this in detail. So let's start in the initial configuration. So in the initial configuration, we have this triangle wherein, okay, let me use a fresh page for this problem, okay, because this concept is much more general than this problem itself. So let's say we have this triangle, right? And now we had these 3 points, A, B, and C. And initially, they are all moving towards each other along the sides of this triangle. So let us compute what is the rate at which they are moving closer to each other or further apart from each other. Okay. So essentially, let's take these 2 points, let's say A and B. Okay. So A is moving along this direction, AB. Okay. And B is moving along the x-axis. So let me actually create this axis also. Let me call this the x-axis and let me call this the y-axis. Okay. Now, essentially, if we now compute VBA, which is essentially VB minus VA, uh, uh, actually, it's better to take B and C over here. Okay. So let's see what is the sort of rate of separation between B and C. Okay. So in fact, actually, okay. So d by dt of RCB. Okay. So this we have shown that this equals VCB, okay, dot ECB hat. Now, how much is VCB? So let's see this. Okay, so VB is okay. So this point B is moving towards C with velocity V. So here essentially velocity of the point B is nothing but V times I cap. Right? And velocity of point C initially is going to have these two components. So this makes an angle pi by 3 with x-axis. So this is essentially minus cos pi by 3 V I cap plus V sine pi by 3 j cap. So we are taking the components along x and y axis. Now cos pi by 3, cos 60 degrees half. So we have minus V by 2 I cap plus V root 3 by 2 j cap. So now if we compute VCB, right, so which is VC minus VB, and we take ECB hat. So ECB hat is nothing but I cap. So this is nothing but I cap, and this is VCB dot I cap. So I'm going to take only the x components of VC minus VB. And that is going to be nothing but minus V by 2 minus V. Right, this much times I cap plus V root 3 by 2 J cap, right? This dotted with I cap. So I'm going to take the component along the x-axis and I'll only get this I cap component, right? So which is minus 3V by 2. Right? So d by dt of RCB is going to be minus 3v by 2. So essentially, points B and C, the distance is decreasing, and the rate of change of this distance is, the magnitude is 3v by 2. So this is the rate at which the distance between C and D is going to decrease. Now, similarly, for A and B also we can compute, and we'll find that the distance is always decreasing with this magnitude, with the rate being, magnitude of the rate being 3v by 2, and similarly for A and C as well. So essentially, between any 2 points, the distance is going to decrease at the rate of 3v by 2. And even as the triangle rotates further, as we have seen over here, the rate of change of distance is always going to be 3v by 2. Okay. So essentially, even in other why? Because essentially by symmetry, even if you rotate all the sides and all the points, the distances, okay, since because the velocities are always along the sides of the triangle, the rate of change of distance, which is the components of these velocities projected onto the sides, that will always be the same, which is 3v by 2. Now, initial distance we know is between any 2 points, let's say B and C, that is actually, let's say A, that we are given as A, and this distance is decreasing with rate, the d by dt of the distance is minus 3d by 2. So therefore, time for distance to be 0 or distance to decrease to 0 is nothing but the initial distance over the rate of decrease, which is 3b by 2. So overall, you get 2a over 3b, which is the final answer as well. Okay. So now I'll leave you with a couple of homework questions. So firstly, suppose, so from triangle, equilateral triangle, let's generalize this to 4 points on a square. Suppose there are 4 points on vertices of a square of side A, which move towards each other with velocities of constant magnitude v, then compute the time to converge. So question 2, so suppose if there are n points at the vertices of a regular n-gun, okay, which move towards each other with velocity of constant magnitude equals to v, and compute the time to converge. So just the same ideas, you'll have to now generalize to an n-gun. So I'm leaving that as a homework exercise. In the next lecture, we'll again look at a new problem, which has applications in warfare also. So hope you will find that interesting, and that also uses this concept of velocity of separation. So hope you will like that, and goodbye. Take care. Thanks. Yeah, let me know in the comments if you like this video, and also if you are able to solve this homework problem. So let us know if you, and in the comments what is the answer you're getting and if you are facing any difficulty. Okay, thanks a lot. Bye.